So yeah, the first module is about the integration of electricity and transport networks, and it's led by Professor Liana Sipsigan. Liana is an elected fellow of the Learned Society of Wales, currently holds the position of Professor of Transport Electrification and Smart Grids at Cardiff University School of Engineering. She leads the Electric Vehicle Centre of Excellence and is co-leader of the Transport Energy Infrastructure Trust at the Global Centre for Clean Energy and Equitable Transportation Solutions. For over 15 years, he's been a pioneering figure in the transition of electrified transport and is acknowledged globally as an expert in decarbonizing transport through electrification using a whole system approach. She has engaged in extensive collaborations with industry, including a period of secondment at the National Grid under the Royal Academy of Engineering Industrial Fellowship. During this time, she worked in the Energy Insights Department, responsible for future energy scenarios. Professor Liana Sipsigan is currently working together with National Grid Electricity Transmission on projects that investigate the difficulties of electrifying commercial and heavy-duty vehicles, the effects of megawatt charging systems on the grid, and the possibility.
Thank you very much, Dimitris, for the introduction. My presentation is regarding the integration of electricity and transport networks. As Dimitris mentioned already, my research work is covering the integration of electricity and transport networks in a whole system approach, more specifically covering the power system, the impact of electric vehicles charging on the grid, looking at all types of chargers, for example, fast charging, megawatt charging from commercial vehicles, but not looking only at the impact on the grid, but also opportunities for electric vehicles to provide services to the grid, particularly in aggregation, and new business models, virtual power plant and aggregations. Also, the vehicle to grid and second life of batteries for repurpose and reusage as the stationary batteries. For the charging infrastructure, my research is covering also the wireless charging, dynamic charging on the road of electric vehicles, and also the infrastructure provision in ports and airports. So finally, the integration of electricity and transport networks using multi-agent systems and building digital twins. But because this is such a complex topic, it is really difficult to be solved by using only one discipline, engineering. For this reason, I'm working from more than 15 years now with my colleagues from other disciplines covering environmental, social, economic, data, and cybersecurity. For this reason is the whole system approach. So the first question is why currently we are integrating electricity and transport networks. This is because electricity is used as a transport fuel. Being used as a transport fuel should be available at any time, and for this reason there are a lot of challenges. In the past, these two sectors were completely disconnected. Now we need to connect them through electric vehicles at all sizes, from private car, commercial vehicle, buses, and even construction vehicles. So the link between these two are electric vehicles. At the same time, the power grid is under a lot of stress because there are some other transport sectors that are using electricity. For example, maritime, aviation, rail, and in parallel, it is also the electrification of heat. So for a traditional power system that was built from bulk generation through the transmission system, distribution system, down to the consumers, that there are houses, commercial buildings, now is becoming such a complex sector. So I mentioned about maritime. We are talking about electric ferries. We are talking about megawatt chargers installed in ports. This is the British company Aqua Superpower, and they have these megawatt chargers for boats, small size, medium size. So only to show you that it is much more complex that road transport. That is the focus of this presentation, and also the focus in the center. So considering these infrastructures in separation, as I mentioned, the electricity system, the transport system, we need also to integrate the intelligence and the communication infrastructure. Because comparing with very traditional going at the pump station and fill your car, when it is a charging event, there is all the time an exchange of data. So for this reason, we have this intelligent and communication infrastructure. In parallel with all of this, the electricity market that was very traditional now is becoming more complex. So in this market, we are integrating ancillary services market, but also new business models and new entrants. And these are the virtual power plant and aggregation. So in this case, these are competing for the same resources and are accepted now as competitors in the electricity market. So what we are doing is to bring all of this together, and from this moment is becoming very complex to address these challenges. One point of complexity is to ensure the resilience of such a complex network, because electricity is a strategic resource. It is with national security implications. And the big question is, who is responsible now for infrastructure security when we are talking about highly decentralized model? Maybe in the next school will be for my colleagues to answer some of these questions. Also, I like this figure. This is coming from the European Smart Grid standardization. And this is showing the evolution of the power system. So in 19th centuries, it was a decentralized power system where there were pockets here and there of electrification. At the beginning of 20th century, it was the unification of all of these pockets, microgrids, and evolved the power system in 20th century as a centralized power system. Now, we are in 21st century, and we are moving back on a decentralized power system where we are building microgrids, balance systems, virtual power plant aggregations, and aggregators, and we are somewhere now at the boundary between decentralized and centralized power system. For this reason, I said the resilience is a really important topic, because everybody is expecting to have electricity at all times. This is a very complex topic, and in such a short period of time, it is really difficult to cover all topics. So my choice for today is to show you the complexity of the electricity system operator to balance the demand and generation. But as I said, this is very complex. The power system is very complex. Actually, I'm teaching 4 modules related to this topic. So let's see this complex role of the electricity system operator. The main role is to balance generation and demand, and this is second by second in real time. It is allow only plus minus 1% deviation from 50 Hertz system frequency, And this is done, as you can see, by a continuous monitoring of the frequency. There is here a snapshot from yesterday. As you can see, the variation of the frequency. If demand is greater than generation, we are expecting the frequency to fall. If generation is greater than demand, the frequency rises. So as I said, a complex, a challenging duty for the electricity system operator. Very simplify how this is done. So this is done by forecasting the load or the load that it is connected in the power system. And there is a lot of experience, of course, in the past with a lot of historical data, and this was forecasted with high accuracy. Then it is allocation units of generation, and this is based on cost. That means the base load is run using nuclear power station and coal for countries that are still using coal. We are free of coal from October last year. Because these generators are expensive to start, stop, so it is not good for the cost point of view. So it's better to run them on a long period of time. When there is an increase in the demand, that it is, for example, in the evening, this is managed or balanced using natural gas generator. These are cheaper start, stop, start, stop. So multiple operations, but costly to run in the long term. Very simplified. It's much more complex than it, but for you to understand. Also, as you can see, there are a lot of variations of the frequency, and the electricity system operator has a lot of contractual agreement with different assets, generators, storage, the demand, in order to stay on a standby and respond quickly and sometimes very fast in order to help this balance that it is in real time. So these are on a standby. This is very simplified, this procedure. Let's consider that there is here a demand curve hour by hour with the traditional one peak in the morning and the second big peak that it is in the evening. So these hours are actually rearranged in order to understand how many hours we need to run, or electricity system operator needs to run certain generators. So as you can see, there are 4 hours that they need to run most expensive electricity. The other is the base load and intermediate load. The other graph, as you can see, is in the mirror, is showing exactly what type of generation is allocated, nuclear, and finally, for this short period of time, combined cycle natural gas and open cycle national gas. This graph is really important for us here in Europe to understand why the price of electricity is high, because actually the wholesale price of electricity is set by the most expensive method needed to meet the demand. So this is gas, to burn gas. And we know all what happened in Europe. We know all what happened with Russia gas. So it is interesting that price of electricity is set on gas prices. So only for you to understand a little bit why we have these fluctuations in the prices this day. So I mentioned traditionally the electricity system operator balance the generation and the demand, you looking at the large power generation and then the well-known demand. Now the problem is becoming more complex because at the demand side, as you can see, we have now electric vehicles. These are charging on the grid. On the generation side, we have stochastic generation that is coming from renewable generation. Wind generation This could, for example, change the power output minute by minute. And then we have a lot of solar generation. This is very popular. And in this case, these are introducing new challenges. And also in the middle, we have now an energy storage system trying to balance this. So it is a very popular resource now in the power system. I mentioned about the solar generation because this is not centrally planned and not centrally dispatched. That means the electricity system operator don't have visibility where there are spread, geographically spread. So what the electricity system operator can see is the net demand. That means the total demand that it is on the power system minus the generation coming from solar. We have here this at the end evolution of the demand curve, and traditionally it was with two peaks, one small in the morning, one in the evening, and this is looking like a camel. This analogy with animals is coming from independent system operator of California, and as the year are passing, they realized that because of this large development of the solar power, this demand curve is reducing in the midday, in sunny days, and suddenly is looking like a duck curve. And now this is well known worldwide as a duck curve, is also here in UK and many other countries. Okay, the system operator is now managing the duck curve. In another diagram, the legs of the duck at least are the base load. So fine, at least we are managing the base load, and we don't need to shut down and restart these large generators. Unfortunately, in these years, as years are passing, we are going off what it is now a canyon demand curve, and this is more difficult to manage. So we are reaching this canyon demand curve also in Germany, of course in California, in Hawaii is also negative. That means we have more generation the load. Because we are at this topic of integration electricity and transport network, we can see now a lot of opportunities for electric vehicles, as you can see here, in order to help with this problem of the duck curve or canyon curve. So if we have aggregation of electric vehicles charging in the midday, when we have this excess of solar generation, in this case could help this demand curve that it is very difficult to manage by the electricity system operator. So could be a positive role for electric vehicles. Now I mentioned about this continuous monitoring of the frequency and different mechanisms that the electricity system operator have to keep between these very strict and tight limits, plus 1%, minus 1%. 50 hertz, it is here in Great Britain, Europe 60 hertz in US. Any deviation below this limit is causing blackout events. This was the blackout event here in Great Britain in August 2019. This is because of the weather. There was lightning strikes. It is a little bit more complex, but it's difficult to explain all of this. And for this reason, were lost generators. If you are looking at the timeline, it's not even seconds here. There are milliseconds. It is such a fast developed event that it was really difficult to manage losing so many generators, and it was not time or properly load shedding to reduce the load in some parts, and it was this blackout event. Of course, with a lot of impact on the transport, on the trains and all the other transport. Here it is in US the same year, but with a much larger disruption. In South Australia, it was a bigger event, and this was called Black System event because, as you can see, the frequency was down to zero, so it was completely disconnected. South Australia, because of some tornadoes there, and as you can see, the overhead line, the transmission system was completely down. And again, if you are looking, I'm not sure if you can see, there are milliseconds there. It is such a fast event that is really difficult to manage. So if you want to practice and to see how difficult it is to keep this balance, you can go at the interactive game. This is set by our electricity system operator. You will receive some small instructions how to do, and you will see that it is really difficult with such high speed to balance the grid. You will receive instruction that we are at this time we are having an increase on the load, then it is the weather, that it is a windy, maybe you have more wind on the grid, so go there when you have time. It's quite an interesting game, interactive game, and also to understand the difficulty to manage the grid. Now we are looking at the impact of electric vehicles on the grid. And this impact of electric vehicle charging is actually a combination of spatial temporal dimension. So why this is the case? Because it is important to understand when these vehicles are charging, at what time and for how long, where they are charging, the location on the grid, and how much electricity the vehicles are using. So this is giving us the magnitude of the impact, and this impact could be at the distribution level, transmission level, and as you can see in aggregation at the electricity system operator level. So why electric vehicles are posing these challenges? Because the power grid was used to manage load in a house, load in offices, in supermarket, commercial buildings, and also industrial load. All of these are fixed load. So these are in a fixed location. What happened with electric vehicles is that for the first time, we have a mobile load. That means the same vehicle, a private car, is charging during night at home. Then is going to charge at the office or in supermarket, or is charging en route if it's going on a longer distance. So the same load is moving in different parts of the network. So this was the first challenge that I'm working to address for 15 years, different levels, different vehicles, different impacts on the grid. But this is the big difference, fixed load versus mobile load in the network. Another point is what demand we are expecting from electric vehicle charging. This demand and the impact at regional level and different clusters in the network is depending on the behavior. And this is something that you will learn later. If people are coming home and plug their vehicles at the peak time when there is a peak of the demand, it will increase significantly this demand. But if this demand is shift and people are waiting a couple of hours and plug their vehicle later. In this case, could be a big help for the grid. And this is called smart charging. Smart charging could be done automatically if the customer is enrolled in a program, such program, or is in an aggregator, or could be simple a behavior change. This was a trial at the national level, the behavior change, in the last 2 or 3 years. And at the national level, during peak time in the winter, the customers were asked to use their heavy loading in the house, not in the peak hours, and it was a big saving for the national grid. So this was a behavior change. Everybody was asked if you can, for example, participate in such a program. If they are charging during midday, in this case will be increase in the midday, could help if we have an extra solar generation, or could have, or if they are charging, fast charging on the road, there is this spike in the demand. This is again not something that the system operator is used, because could be this spike in the demand for a short period of time. 20 vehicles are in the charging hub and are charging all for half an hour. So in this case are inducing these spikes. A second important topic here is to understand the demand curve for megawatt charging for charging commercial vehicles. Commercial vehicles are, let's say, much easy to follow, because a fleet of vehicles is with a fixed route, could charge at the depot. As you can see here, there are clusters of depots. Not happy for the grid, because in this case could have a big impact or request of electricity in these clusters. So this could be a slow charging, could be also a depot fast charging between shifts, and also en route charging, in this case using megawatt charging. This is a new standard, and this is a new type of vehicle charging. Also, if you are following the news, you saw a big announcement by Chinese, of course, car manufacturers, that they will produce by the end of this year megawatt chargers for private cars. It is a big question, and they said that they want to charge in 5 minutes. It is a question on the behavior change, why you need to charge in 5 minutes comparing with 50 minutes that is now offered by fast charging. And the big issue is what happened with the battery and the battery degradation, but their stakes are higher now, and Tesla down and so on. It is some kind of game at the moment, or competition. But the question will be how this high current, high power will be the impact of the batteries, and why we need this. Also, for commercial vehicles, there is a mandatory travel and break. This is coming from UK government, so 9 hours maximum for travel, and then 45 minutes break, but there are different combinations. So it is much easy to understand where these vehicles are charging. And as part of one of the National Grid project, we are producing these demand curves. We have different tools here in order to understand how this look like, and also how this look like in aggregation. If, for example, we have a depot close to a charging hub, in this case, we could have a big request for the demand. This is the aggregated demand. Couple of more minutes only to finish this section. Now, this was an aggregated demand. If we want to understand more granularity, how demand look like, we are using multi-agent systems. These are, we have different models, quite advanced model built by our colleagues in US. Also, we have a model for UK. That means we have the agents. These agents are built with attributes from commercial vehicles. So we populate with the capacity of their battery, range, consumption, speed. And we are moving these agents on the road. We have agents for the charging station and more other attributes added like climate condition, vehicle condition, payload, and also driving cycles. Our colleagues are quite advanced in populating these agents. So in this case, what we can record is the battery state of charge in real time as these vehicles are moving on the roads. And in this case, to understand the energy requirement, where it is a requirement for this charging infrastructure to be installed in order for commercial vehicles to charge. So similar is a similar model that we have for buses. Here we have different charging options and the state of charge of the battery, and also the energy requirement. So for the buses also, we are looking the number of passengers on each station based on some historical data. So these are quite advanced models, giving us much more granularity than the other models that are looking with different levels of aggregation at different parts of the network. So these are, I will finish the class soon. So these are actually the input in our models where we are integrating electricity and transport networks. So we are looking where these vehicles are moving on the road and what electricity infrastructure we have in these locations where the vehicles are charging. So in this case, we are looking at this clustering impact on the network. So we are working close with National Grid, and we have different models for this. Finally, I finish with this one, that it is not only impact on the grid, but we are working quite a lot how electric vehicles can provide services to the grid at different levels through these new business models and services. And this was a virtual power plant that we've built with colleagues from computer science in a project in order to manage through vehicle to grid the high price of electricity that it is for the buildings, and to power the buildings vehicle to building through vehicle to grid. So maybe on another occasion to go in more details. It is the same principle at a lower level that it is applied at the system operator level to match generation and the demand, and also to forecast the demand. Finally, I want to state that vehicle to grid was used quite a lot in US when there was this extreme event. It was monitoring by Ford, by Tesla, how many power the buildings through their vehicles. So again, it is a behavior change is good when there is such extreme event to wait the event with your battery fully charged. So in conclusion, electricity is used now as a transport fuel. Very difficult to have this complex management of electric vehicle fleets. But it is important that this is not a revolution.